Alright, today I'll be talking about periodic trends, electronegativity, atomic radius, ionic radius, ionization energy, and so much more. And as I said up here, it will require absolutely no memorization. So what exactly does that mean? So I'm basically saying that this is, the way I like to think about it is just common sense. I'll go into more depth into this as I go along with the slides. And the more problems I do, the more you'll understand how this is quite literally common sense. But to fully understand this, some background information is that positive attracts negative, so positive and negative attract. So what that basically means is you've got the positive nucleus, you've got the negative electrons, right? And here's another model. Which one's going to have greater attraction? This one or that one? Well, it's going to be this one because they're closer together, so they're going to have more attraction. The way I like to think about it is magnets and a book. So let's say you've got a very thin book, and here's a paper clip. And here's another magnet, and it's an extremely thick book. And here's a paper clip. Basically, the magnet is the positive nucleus, the paperclip is the negative electrons, and this book is just the space between the nucleus and that valence electron. So the more space, the more stuff that's in the way between that positive nucleus and the negative electron, the less attraction there's going to be. Okay? And that's just the common sense that I want to make sure you guys understand for the continuation of this lesson. Alright, so I'm going to start off with atomic radius because almost everything is based off of it. So for atomic radius, it's most likely to say it's the radius from the nucleus to the outer shell, but as we know, we don't really know where the valence shell ends because it's a cloud. So what's actually the scientific definition is the distance between two nuclei of the same bonded atom. So let's say this is sodium, divide that by 2. And this is a very popular test question, so make sure you get it. This is not the correct definition because, again, atoms are clouds. We don't know where that valence shell ends. So the actual proper definition is the distance between two nuclei that are bonded together divided by 2, and it has to be the same atom. Okay? So the trend for atomic radius is this. I'm going to first dodge arrows and then I'm going to explain it a bit later. Something with my arrows, I'm drawing them where they're increasing. So right here, this would be increasing. And the down arrow would be an increasing atomic radius as well. For me during tests, I always like to draw a little mini periodic table. It helps me a lot. I'll get to that a bit more in the end of the video. So it's just some test taking strategies. Well, anyways, for atomic radius, it's imperative that you know what a period and a group are. Well, down here, each one of these are called groups. This is group 1, group 2, group 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Group 18 are the noble gases. This is the alkaline metals, alkaline earth metals, halogens, noble gases, and all that. Those are groups, okay? And as you go down a group, so this way, as you go down the group, you're increasing in a period. Okay, so let that sink in. Because this is period 1, period 2, period 3, 4, 5, 6, 7. So when you're going down a group, you're increasing in that period. Let me put the periods in a different color so it would make a bit more sense. So when you're going down a group, when you're going down a group, you're increasing in period. So 1, 2, 3, 4, etc. And periods represent the number of valence shells. So this is 1 valence shell, 2, 3, 4, and so on. So when you're going down a group, you go from 1, 2, 3, and 4, and so on. And is this getting smaller or larger in atomic radius? Well, it's getting larger. So that's how I like to think about it. When you're going down a group, you're increasing in period, you're increasing in the number of valence shells, number of energy levels, meaning you're increasing in the size because there's more and more shells. So like 1, 2, 3, 4. Okay? And for going across, this one's a bit tricky, but not that much. It will make sense. So this, you're in the same period, but you're in different groups. So this, you're in the same period. Periods go this way. You're in the same period, but when you're going across that period, you're going from group 1 to group 2 to group 3, 4, 5, 6, 7, etc., and so on. And when you're increasing, what do you notice? Well, look right here. What's happening to the number of protons? They're increasing, right? So when you're going across, there's an increase in the number of protons. And when there's an increase in the number of protons, there's an increase in the number of electrons, because we're assuming these are neutral. And when there's more protons and more electrons, there's more attraction. There's more magnets. And it's going to make it smaller, because let's say we're in the 4th period right now. So we're right here. Right here. Let's say we're in the 4th period. So exactly where I have highlighted in yellow. That means we have 4 shells. So 1, 2, 3, 4. And as we're increasing the number of protons, the number of electrons. So there's going to be a more force of attraction. There's going to be more protons pulling on more electrons, making it tighter and smaller. So when you're going this way, it gets smaller because there's more protons, more electrons, more magnets. That's how I like to think about it. Meaning it increases going that way. I know that might be a bit confusing flipping it in your mind. So if you want to think of this arrow as going that way and saying decreasing, then you can. And then you can just flip it around if you want increasing. So all in all, basically atomic radius is going to be the largest around this area because it's increasing this way, increasing that way. Okay? So now I'm going to go on to ionic radius. So ionic radius is a bit relative. It's all you have to know is you've got anions, you've got a neutral atom, and sorry, the noise. We've got a neutral atom and you've got cations, alright? So for anions, they have a negative charge. Cations have a positive charge, and neutral is just neutral. So let's just say we're talking about an element of sodium. So you've got sodium minus, sodium plus. Okay, think about it this way. When you're adding an electron, does it get bigger or does it get smaller? You're adding electrons, right? So it's going to get larger because you might be adding one more shell. There's going to be more repulsive forces between two electrons, so it's going to be bigger because it's the same number of protons because it's still sodium, but you're adding more electrons. Even if adding an electron might not lead to another shell, it's going to lead to an increase in repulsive forces between electrons. So the electrons are going to pull away from each other, making this bigger. Okay? But when you remove a electron, which is this is not adding a proton. Remember, this is removing an electron. When you remove an electron, it's going to be smaller. Even if you're not removing a shell, you're still removing one of those repulsive forces, meaning the proton doesn't have to fight that much to keep everything together. It has less protons. It has less electrons that it needs to keep inside that atom so it can keep everything tight. So it's just a relative force. Know that anions are larger than their neutral counterpart and cations are smaller than their neutral counterpart. Okay, now I'm going to electronegativity. So electronegativity is the attraction to an electron. So how much an atom wants an electron. Okay, so we're gaining electrons. This is not like ionization energy where you're losing one. I'll get to that in a bit. But electronegativity is where you want an electron. It's from a scale of 1 to 4, and it's the opposite of atomic radius, and I'll explain why. Meaning that it's increasing when you go this way. So this is increasing, and it's increasing when you go up. So this is increasing as well. Alright? Sorry, I spelled increasing wrong. And the reason that is, so let's just say we have a small atom and we have a large atom. We've got this, and we've got that. Okay? So I'll put my shell to make it look bigger. So you've got a proton and you've got electrons around here. You've got protons and you've got the electrons. I'm only going to be thinking about the valence electrons because those are the actual ones involved in bonding, and that's what we care about. So when an electron comes in, it's going to come to the outer shell, right, to the valence shell. But look how far it is from the protons. The proton's not going to want it that much. Think again about our image of the book and the magnet. The thicker the book, the thicker this is, the longer the distance, the less it's going to want that extra electron. So the lower the electronegativity is. But the smaller it is, when an electron comes, it's going to come in a very close shell towards the nucleus. So the nucleus is going to want that extra electron. It's going to want to be more attracted to it because when the electron comes, it's already going to come close to the protons. It's not like it's going to come 3 shells away from the proton as from the nucleus as in this example. So it's going to be less space. It's just going to be this much. All right? So what does this have to do with ionic radius? Why is it the opposite? Well, the larger the I'm sorry if I said ionic radius. I meant atomic radius. The larger the atomic radius, the less the electronegativity. Because it's going to want that electron less because it's farther away. It's not going to be as attracted to it. But the smaller the atomic radius, the greater the electronegativity, because that nucleus is going to be closer to the valence shells and to other possible electrons that could be entering. So it's going to want that other electron. So that's why it's opposite. As while atomic radius was increasing this way, meaning as it gets smaller right here, so that means right here is the small area, and this is the large. The electronegativity is going to be the opposite, meaning it's going to want to go to the small atoms, as we saw right here, compared to the large ones. And that's going to be the same being true for going across a period. Here it's going to be the small ones. Here it's going to be the large ones. And that electronegativity is going to increase as you get smaller because that nucleus is closer to the valence shells and it wants that. All of this is really common sense. As long as you know your atomic radius, you're pretty well fine. You don't necessarily have to memorize it. That's my thing about memorizing things. I just don't like to waste my energy space. You can just remember that when you're going down, it's increasing in shells. When you're going across, more protons, more electrons, more magnets. And that electronegativity is going to be the opposite of atomic radius and ionic radius. It's just really going to depend on the other atom that you're comparing it with. In ionization energy, this one's a bit tricky. So ionization energy is how much it wants to lose an electron. So the energy, it's a measure of energy. This was like the measure of how much it wants it, not really value. It's just like a 1 to 4 type of thing. But ionization energy is the energy required to lose. It's the energy required to lose an electron. Sorry, I spelled lose wrong. To lose an electron. So think about it this way. Okay. The energy required to lose it, meaning the higher the ionization energy, the harder it is to lose that. Let's say you have an ionization energy of 20 versus 130. Which atom is going to be less likely to lose that electron? This one. because it requires more energy to remove that electron than the 20 value right here. And it's going to be the same trend as electronegativity, which is what confuses most students, because they're like, wait, it's the opposite. Wants electrons, energy required to lose electrons. How can it possibly be the same trend? Well, their value that they represent is the opposite, because the higher this is, the harder it is to lose an electron. But the higher this is, the easier it is to gain an electron. Okay, here, I'll get into it now. So for ionization energy, it increases going this way, and it increases going this way. So this makes sense because let's say you've got a small atom and a large atom. Okay, so you got your protons here, they're positive, and you've got your electrons out here. So which one is gonna lose that electron easier? The one where they're very far away and it doesn't really care what's going on there because it's not attracted to it either way, or the one that's very close to its valence shell and it wants to keep those electrons? It's gonna be this one. This one's gonna have a low ionization energy because it's going to be easier to remove that electron because they're far away. They don't have a great attraction anyways. Again, remember the magnet with the paperclip. It's going to be farther away from the paperclip, so it doesn't really care if you lose it because it wasn't attracted to it in the first place. So it's very easy to lose it. It requires just a little bit of energy just to tuck it out. But if you had all of this gone and you just had this area right here, a very small textbook between the magnet and the paperclip, then it will be attracted to the paperclip more because it's closer to it and it will require more energy to remove the paperclip. So a small atom will have a high ionization energy because it's closer to its valence shell and more attracted to its electrons, and it doesn't want to lose it. So basically, from small to big, see how everything's connecting to atomic radius? That's why I say it's very important to get your atomic radius correctly. So it's going from big to small this way, and it's big to small that way. So the smaller it is, the higher the ionization energy because it requires more energy to remove that electron. But, and again, right here, the smaller it is, the more ionization energy it requires to remove that electron. Alright? So here is one last periodic table to summarize everything up. So atomic radius, it increases when you go this way. So here it's increasing. And it increases when you go that way. And for electronegativity, it's the opposite. It increases when you go that way. And it increases when you go this way. For ionization energy, it's the same trend as electronegativity because remember they represent opposite values. It increases going these ways. Increases. Alright? So green is ionization energy, blue is electronegativity, and red is atomic radius. There's not really a trend for ionic radius because it's really just a comparison between a neutral atom, a negative counterpart of that, and a positive counterpart for that. Alright, that concludes my video, and I hope it was helpful. If you have any recommendations, please let me know in the comments below. And as always, thank you for listening, and please subscribe.